So if you go through the process of factoring this fully, you would have got that this is equal to x plus 2, x minus 2, x plus 1, x plus 1. And if you were going to graph that using the factoring method, you now know 3x intercepts. Our x-intercepts happen at -2, 2, and 1. We've got -1 and +2. And if we look at this is an x to the 4 graph with a positive leading coefficient. So its end behavior is going to act like a parabola. The other thing we could find is if we plug in 0 for x, we could find out that our y-intercept happens at -4. So now, going about graphing this, we know that it has to start up here. And we know that it has to end up here. And if we're going to go through all of those points, well, I'm going to have to go down through this one. Then I need to go up through this one. And now it sort of seems like I'm in a little bit of a bind. I need to go through that other x-intercept, and I need to go through the y-intercept. So the way that I've drawn it right now, well, maybe I could just sort of, can I loop around and go through that? Is that okay? Maybe this is a new kind of polynomial function we've never seen before. But no, all of a sudden, that doesn't pass the vertical line test, and that's not a function. So we're going to have to erase that. Whoops, that's not erasing it. Wow, we're having issues. There we go. Let's see if I can still go back. There, nice. Go back again. Perfect. So we're going to start up there again. Any suggestions how I can go through all of those points without adding a new x-intercept? Because I mean, I could have gone. Whoa, here we go. Slowly. Are we? Oh, technical difficulties. Here we go. All right, I could go through this point, up, down again, like that, but then I invent a new x-intercept that doesn't exist. So that's a problem as well. Yes, suggestion. Okay, so we could go down like this. We could come touch this x-intercept but not cross, still go down like that and through. And that is, in fact, what this graph will do. Now, so something weird happened at that -1, where it just touches the x-intercept but didn't go through. If we look at the factored form, what's weird about that x-intercept? Or what's different about it? In fact, I could rewrite this equation as f of x equals x plus 2, x minus 2, and the x plus 1 happens twice, so I could say that it's squared. So we have the x plus 1 factor twice, and on our graph, that shows up as it just touching the x-intercept and then not going through. So some different things happen when we have the same x-intercept or the same factor more than once. And that's what we're going to learn about today. So if you could turn to, I think you have, we're in 1.4, we're just about at example 3. If you could turn to page 44, you have some space on the column of page 44 on the left. And we're going to add the following note. So the example that we had was an example of a root having an even multiplicity. Multiplicity refers to a factor happening more than once. And in our case, our factor happened twice. So whenever a factor happens either twice or 4 times or 6 times, whenever that power of that factor is an even number, we say that it has an even multiplicity. And whenever we have a graph with an even multiplicity, what's going to happen is the graph is going to bounce at the x-intercept. So just like ours touched the x-intercept and went back down, it won't go through at that x-intercept, but will bounce off at that x-intercept. And if we have an odd multiplicity, the graph will go through the x-intercept. But something happens if the odd multiplicity is like a factor like x plus 3 to the 1, just happening once. That's the ones that we've had mainly so far. So if the multiplicity is 1, it just goes straight through. If the multiplicity is bigger than 1 and still odd, in other words, 3, 5, or 7, and so on, in those cases, it goes straight through. Well, I won't say straight through. I'm going to say that it bends. And goes through. And you already have one of your parent graphs from transformations, our very first unit, had an odd multiplicity bigger than 1. If you think about your x to the cube graph, your x cubed graph, you could write that as x plus 0 3 times. You have the same factor 3 times. And what did that graph look like? Well, it had only one x-intercept right at 0. And what happened at that x-intercept? Your graph bent at that intercept. So we're going to start to see certain graphs have points where it bends at, certain graphs have points where the graph bounces off of, and so we're going to use that as another technique for graphing our polynomial functions. So if we go to example 3 now, the nice thing about example 3 is they're already pre-factored. So you already know where the x-intercepts are going to be. So when we go to sketch this graph, we know that there's an x-intercept at -1 and at 2. If we plug in 0 for x, we're going to get a y-intercept at -2. Now to figure out the end behavior of this one when it's already in factored form, here I have x plus 1 to the 4. Does it make sense that that will give me an x to the 4? And here I have another x minus 2. That will give me another x. If I multiply that x to the 4 by the x, this is going to be an x to the 5 function with a positive number in front. If it's a positive number in front, it's going to act like a line, and its end behavior is going to look like that. So we know that our graph starts from down here, needs to end up here. What's going to happen at -1? It's going to bounce. So when we get to -1, it bounces off of there, needs to go through that point, and at 2, it'll go straight through without a bend, because we can say this has a multiplicity of 1 because it would have an exponent of 1. That factor happens only once. Now when you're drawing your curve, you need to have it go through, obviously, all of your intercepts, and you're going to try to draw your curve with a smooth curve as much as possible. So I went through this point and I felt like I needed to go further down before I looped up. That felt most natural when drawing it as smooth as possible. But if you had decided on this as your graph, that would have been given full marks. So as long as it's going through those points, it has the right end behavior, it has the right things happening at the intercepts, whether they bounce or whether they bend or go straight through. How far down doesn't really matter. If we wanted to be more accurate, we could go to our table of values technique. And we could say, I'm really curious what happens when x is 1. And you could plug 1 into the equation and find out that it's equal to -16. And then realize that both of the graphs so far weren't very accurate, and that it should look way down there before coming back up. But any one of those will be fine, and that extra point, although it makes it more accurate, isn't necessary to get full marks on a question like this. It's just asking for a sketch. The graph wants you to go through your x-intercepts correctly, go through your y-intercepts, and have the correct end behavior. Once you take calculus next semester, if you haven't signed up already, make sure you do that. Once you take calculus next semester, you'll find out in calculus we are able to find out where these minimum points are, what their exact values are, and techniques. But this unit is really setting us up for that in calculus. So for our second graph, again, it's already in factored form. We can set up our axes. We know that we have an x-intercept at -1 and 1 at 3. If we plug in 0 for x, we'll get a negative times 1 times -3. And we'll get our y-intercept at 3. Number one place that people make mistakes in this unit is in calculating that y-intercept. Sometimes you just forget a negative sign, or sometimes a negative value gets squared, but you don't get rid of the negative. And so if all of a sudden what you want to graph with all the end behavior and the bounces and the bends is not working with your y-intercept, it's probably telling you made a little mental math error in calculating that. Now with this function, we've got 1x here, which will be positive. We would have x cubed there, which would be positive, but we have a negative out in front. Putting all of those together, this will act like a negative x to the 4 graph, so its end behavior will act like a parabola. So we know that our graph is starting down here and going to end down there. What's going to happen at -1? We'll go straight through. Will it bounce or will it bend? It'll bend. So when we're drawing that, draw our bend through this point, and at 3 it'll go straight through. And we have our graph. So we're going to take some time to practice those right now, questions 9 to 12.